Hello, friends. This is Jim here with Science Talk. And in this video, I'm going to discuss with you rotating systems. This will include a discussion of high and low pressure systems, the atmosphere, as well as oceanic gyres. I'm doing this video because in preparing the videos addressing um, the oscillatory systems of the planet, and so the North Atlantic Oscillation, Pacific Decadal Oscillation, etc., that there's a lot of mention in those videos of high and low pressure systems and gyres and etc. So I thought it'd be worth it the while to kind of do a lengthy video and at least give you a basic foundation of what's involved with them. So, having said that, uh, let's get into it. So, gyres and other rotating systems, such as cyclones and anti-cyclones, which are low and high pressure systems, respectively, are formed as a result of several factors coming together to help form the system. Typically, it involves pressure gradient force, whether it's in the atmosphere or in the ocean. A pressure gradient force sets things in motion. Involves what's called a geostrophic flow. This is especially true for oceanic gyres. The Coriolis effect, note it's effect, not a force. Another thing called the Ekman spiral and the Ekman transport. This is extremely important to understanding how gyres form, but also with coastal dynamics. For example, a coastal upwelling and coastal downwellings, all involved with the Ekman spiral and Ekman transport, which, as we will discuss later on, is really all the result of wind forcing. Then there's the curl. Now, the curl is not what you do, with your arms like that. But curl is a very specific mathematical concept. It involves the result when two vectors are crossed. It's called a curl. So we'll be talking about that, and as well as the results of these machinations, which includes divergence, convergence, updraft, downdraft, upwelling, and downwelling. Updraft, downdraft refers to atmospheric motions. Upwelling, downwelling, the same idea, but involving oceanic movement. These rotating systems affect our weather, ocean productivity, even concentrating plastic garbage in the ocean. And then weather oceanic gyres are driven ultimately by unequal solar heating and cooling. Okay, so here's the general background of the major atmospheric circulation. So we'll start at the equator, 0 degrees. And you'll note that on either side of the equator, you have a Hadley cell. Now, Hadley cell, these are convection cells in the atmosphere. These are vertical convection cells. So we have a Hadley cell that straddles either side of the equator, over here as well, across the whole planet, all 360 degrees of it. And basically, in between the Hadley cells is a low pressure system. You note with the low pressure system that it is rising from the ground. So it rises because it's warm air. So the magenta lines indicate warm air. The blue lines indicate cool air. As the warm air rises, it cools and it starts to sink. Up here is a divergence. So it's diverging this way, flowing outward from the center, and then it cools and it sinks. And it sinks down here. So where the Hadley cell meets what's called the Ferrel cell, you get a high pressure system. It's high pressure because the air sinks down it, exerting more pressure on the ground than at the low, where it rises, lessening the pressure. And then between the ferrule and the poles, you have what's called a polar cell. As you can see, it's mostly cold air, which makes sense. So you'll note that look at the direction. This is rotating in that manner. This is rotating in that manner. So you get an alternation of low, high, low, high, low, high, low, high as you go from equator to pole. These are the trade winds. Northeast from the northern hemisphere, southeast from the southern hemisphere. Then you have the westerlies, right? So they blow in that direction. So a little note thing about how we talk about wind flow. The winds are identified by the direction they come out of. So northeast goes from northeast to southwest. Southeast trade winds go from southeast to northwest. If we're talking about western currents, that's because they're flowing in the west from east to west. It's kind of crazy. It's confusing, I know, but I did not come up with the system. So the westerlies come from the west and they flow to the east, the winds. A western heading current comes from the east going to the west. You just have to kind of keep track of it. And then we indicate some polar jet streams here. You got the polar easterlies, which is some really dense, cold, nasty stuff coming down. And then you have from both the Antarctic and the Arctic area. And of course, you're going to have the equivalent of this westerlies in the southern hemisphere. So basically, we're going 0, 30, 60, 90 degrees as far as the latitudes go. This wavy line indicates the polar jet streams. This wavy line is a subtropical jet stream with the mirror image on the southern hemisphere. And so that's about, it kind of gives you a general overview. This gets into a little more detail. So you see a subpolar low pressure, a tropical high pressure, which, is subtropical high pressure, subpolar low pressure right there. And then the equatorial low pressure, the doldrums. Oftentimes ships sit there and they don't move. And back in the days of the sailing vessels. At 23.5, you have the Tropic of Capricorn. At 23.5, you have the Tropic of Cancer. That would be north and south latitudes, which this is not set in stone. This changes with the tilt of the Earth's axis because Tropic of Cancer typically define the position of the sun in relation to, where it rises and sets throughout the course of the year. I also stay here, note the equatorial low also corresponds to the intertropical convergence zone. Even though, as we'll see, because it's converging due to the air being pushed this way. And the air being pushed this way, if you remember from the ENSO slides, this is going to drive the water to the west, piling up the water here, and depending what state of El Nino ENSO you are in will determine what the conditions are for the rest of the Pacific. But it's the intertropical convergence zones due to the air movement. As we'll see when we get to gyres, you actually have an equatorial upwelling here because of the behavior of the gyres. So that's coming later in this video. So I wanted to indicate this, showing prevailing westerlies, the trade winds, and the subtropical high pressure, something referred as the horse latitudes. Not really sure where that came from. I don't recall at the moment, but there it is. So this is a general idea of high and low pressure systems. For lows, there is a convergence, which is an inflow to the center at base level. Now, a low pressure system, you have warm air rising. That's what these arrows indicate. And it spirals. So you have a convergence at the bottom, a divergence at the top. And it's the opposite for the highs. The highs, you have the air sinking, so you have a divergence at the bottom. So you see the outflow from the bottom, but there's a convergence at the top. And typically, if you look at, watch the cursor here. Think of this as being like the Hadley cell going to the Ferrel cell, right? You have this convective cell in the atmosphere. Divergence at the top of the low pressure system creates a convergence at the top of high pressure system, where it sinks. This flows outward, it flows inward here, etc. Okay. Downward flow of air to lower levels exerts a greater pressure at that level, hence it's called highs, whereas air moving upwards, quote unquote, lightens the pressure, resulting in lower air pressure. Updraft leads to downdraft. Right, and as I said, as I just mentioned, this is how vertical convection cells are created, such as the Hadley and Farrell. So just another diagram showing the same sort of idea. Downward airflow for the high pressure system called the downdraft. Upward airflow, updraft for the low pressure. In both cases, a flow into the center, lows, or out from the center, highs. The air follows the pressure gradient, moving from regions of high or higher pressure to regions of low or lower pressure. Right? This is the key point. Pressure gradient, whether we're talking atmospheric or oceanic. So a little summation of low pressure. Okay, unstable rising air causes unsettled, changeable weather. You get cloudy skies, low levels of sunshine, wet, precipitation, temperatures that are mild for the time of year. Low pressure tends to be a bit warmer because you got the cloud cover. Cloud cover is an insulatory factor. Could be windy. You got wind moving in, and you got changeable weather. Now, here are bars, right? Looks like in millimeters of mercury there. And you notice it's higher on the periphery, lower in the middle. So guess what? It's going to go from high to low. That's why it flows in towards the center. And of course, with as with, always with my videos, you can always pause my videos and examine these diagrams in more detail at your convenience and at your pace as you so wish. Okay, so this is showing low pressure again, following the pressure gradient, moving into the center, and eventually you're going to set up a spiral where it's going to rotate in a cyclonic fashion. Let's look at a high pressure system. Air flows out from the center. It spins clockwise in the northern hemisphere. It's called anti-cyclonic. In the southern hemisphere, it would be spinning counterclockwise. No mixing of the air, stable fair weather, sinking air, there's few clouds, lots of sunshine. There's a joke among airplane pilots, what's the conditions? You have severe clear, then you're flying into a high pressure system. Long duration can result in inversion and pollution. Inversion is where you have basically warmer air trapped at elevation, as opposed to always the temperature decreasing as you go up in altitude. Winter, it's often extreme cold. Here in Alaska, in the days, we don't really get that too much anymore because of global warming. But it used to be that if you have that Siberian high, slide on over interior Alaska and the Yukon, it just sat there and it would just spin and spin for weeks. And for weeks, you'd have 50 below. And all you could do is just wait for that damn pressure system to erode. So we don't get that anymore. Not that I'm complaining, it's good for my heating bills. But still, I mean, you get that Siberian high and you'd be freezing your asses off for a while. So here's a high pressure system, again, diagrammatic. So you have higher pressure in the center, lower outwards. So you follow a pressure gradient, goes out from the center. This is starting to indicate some little Coriolis action, deflecting to the right in the northern hemisphere. PGF, pressure gradient force. Get used to seeing that abbreviation. Deflection to the right northern hemisphere, to the left in the southern hemisphere. We'll be talking about Coriolis later on. So this shows how lows and highs can be tied together, right? You get this kind of a trough line in between the systems here. You get some of the divergence at the surface moving in, and then convergence at the center of a low, with an upper air divergence and an upper air convergence. So this would be a high, this would be a low. Divergence of air aloft causes air to ascend, resulting in low pressure at the surface. Convergence of air aloft causes air to descend, resulting in high pressure at the surface. As air diverges and converges around an upper air low pressure trough, surface lows and highs are generated. So that's why if you look on a weather map, you often see highs and lows all kind of like strung along together as a weather system. They'll follow front lines, what have you. Remember, wind is nothing but the atmosphere in motion. Okay, so so this is basically kind of a summation. I have some more coming on later, but at this point, I wanted to introduce to you what the Coriolis effect is. The Coriolis effect is the movement of wind and water to the right or left that is caused by Earth's rotation. It causes fluids such as air and water to curve to the right in the northern hemisphere in a clockwise direction. The Coriolis effect also causes fluids to curve to the left in the southern hemisphere in a counterclockwise manner. There is no Coriolis effect on the equator. Air or water will flow in a straight line. And later on, I'll show you that you get this wind forcing, and that's what helps drive some of that water towards Indonesia and Australia during the ENSO cycles. Now, here's an interesting historical tidbit. How the Coriolis effect first came to be realized that it's such a thing. It occurred during the Napoleonic Wars. Napoleon was sitting there doing his warring across Europe. He had his cannons, and he wanted to, send artillery shells to the enemies and decimate their numbers and so forth. So he would instruct his, battery people, the artillery people, if you will. Okay, see those people over there? I want you to obliterate them. Aim your cannons and let fly. And they would do so. But oftentimes the distance was such that they kept missing to the right. And Napoleon was getting ticked off. Says, what the hell? Can't you guys shoot straight? And the answer is no, they can't shoot straight, because what's happening is as the shell is in flight, right? So let's say here's the enemy right there, right? The shell's in flight, the Earth does what? Right? The Earth rotates under it. Let me just enlarge this a little bit here. Okay, so this is going on here, right? They're aiming here, so they fired the shell, but this is what the Earth does underneath it. It rotates. So the enemy was originally here, and the rotates are over here. So you miss. There's that curve, the apparent deflection to the right. It's due to Earth's rotation. If the Earth did not rotate, you would shoot straight. You wouldn't have a gyres, most likely. But so it's really something that was discovered during the Napoleonic Wars. So just wanted to throw in that historical aspect. So this is just a quick little diagram showing it from vector consideration what's happening. Again, for the northern hemisphere, Earth's rotation is this way. If the wind direction is that way, the movement is that way. If the wind direction was this way, the movement would be that way, to the right. And then it's opposite when you get to south of the equator. Then you would have the vector diagram would go that way. Coriolis effect is the Earth rotates, winds and currents move in a curved path. That's the Coriolis effect. So the black arrows indicate the path of the wind without Coriolis. This, of course, is representing the Earth's rotation. But what happens here is, so you have wind going this way, winds going that way. So in the southern hemisphere, it would be deflecting to the left this way, to the left this way, because the wind's moving that way, wind's moving this way to the left, etc. And then the opposite in the northern hemisphere. Wind's going this way, wind goes to the right. Wind's going this way, it goes to the right that way. Again, feel free, when you're viewing this, to pause the video and study this. But that's basically what's happening here. So imagine you fire off a shell, the Earth rotates underneath the projectile while it's in flight, and all of a sudden you just wasted some ordnance because you whoppingly missed. Now, I couldn't help myself, but I had to throw in a wee bit of math. And don't worry, it's not too bad. The Coriolis effect is most pronounced, the greatest effect at the poles, where the velocity is minimal but the highest angular momentum. Now, when I refer to the velocity here, I'm talking about horizontal flow. Okay? If you're standing on the equator, if you're standing on the North Pole, okay, here's the North Pole. You're standing right there. All you're doing is you're just spinning in place. You have great high, tight, angular velocity, but you don't have much linear velocity. Whereas if you're on the equator, right, you're just spinning right around this way. If the Earth were a cylinder. Okay? It's least on the equator where velocity is maximal but lowest angular momentum. Mathematically, it is. The Coriolis frequency, denoted by small kz, also called the Coriolis parameter, Coriolis coefficient. And I will tell you, you see Coriolis parameter used 99% of the time. It is equal to twice the rotational rate, omega, of the Earth, or the angular momentum of the planet, multiplied by the sine of the latitude, phi. So F is equal to 2 omega sine phi. The rotation rate of the Earth, omega, is 7. If you want to round it, 7.3 times 10 to the minus 5. This is radians per second. Now, we measure angles in radians, not in degrees. If you want to convert your conversion, if you want to convert from radians into degrees, you multiply by 180 over pi. If you want to go from degrees to radians, you multiply by pi over 180. And as you can see, it can calculate as 2 pi per t, capital T, radians per second, where t is the rotation period of the Earth, which is 1 sidereal day. It's not 24 hours. It's 23 hours, 56 minutes, 4.1 seconds. That's another reason why we have leap years and leap days and all sorts of kind of stuff. We round it to 24 hours, but Earth actually completes one rotation in this indicated time right there. In the mid-latitudes, the typical value for F is about 10 to the minus 4 radians per second. By convention, the equator is 0 degrees latitude. The sine of 0 equals 0. The poles are respectively 90 degrees north latitude, designated as plus 90, 90 degrees south latitude, designated minus 90. The sine of 90 is plus 1. The sine of minus 90 is minus 1. So from these values, you can easily see how there is no Coriolis at the equator. The whole damn term goes to 0. And the Coriolis parameter is part of a larger series, part of a series of larger equations that factor in, basically equations of motion. Okay. I'm not going to go hog wild crazy. I don't want to turn this into a graduate level physical oceanography class, but that is what's going on. Okay, so it's most pronounced at the poles where the maximum value is attained. The plus 1 indicates flow to the right, minus 1 flow to the left. Basically, this calculation right here will tell you how much deflection will occur for a given latitude. The higher you go in latitude, and those are closer to the pole, the greater the deflection will be. Now, here's where it gets a little funky. When you study Calculus 3 and you learn about doing integrals using spherical coordinates, the convention is North Pole is 0 degrees, the equator is 90, and the South Pole is 180. So now you, instead of using sine, you have to use cosine. And it just gets crazy. So oceanographers, atmospheric scientists, astrophysicists, astronomers use the convention of 0 being at the equator, going to plus 90, minus 90. Mathematicians go from 0 to 180. They just want to be pains in the asses. Anyway, but this is why, on the equator, there is no deflection. And when you go to the poles, you have maximum deflection. Basically, is all that little calculating factor is telling us. Now, here's just a quick little scratch of a diagram here. This is a low pressure system. Okay, this is for the northern hemisphere. Higher pressure out at the periphery, lower pressure in the center. So you can follow the pressure gradient, moves in. As it moves in, Coriolis is acting on it, northern hemisphere. The deflection is to the right. You sum this up, and what do you get? For the northern hemisphere, you get a counterclockwise flow. PGF is pressure gradient force, right? You get this counterclockwise rotation that is typical for low pressure systems in the northern hemisphere. It would be opposite in the southern hemisphere. And the blue arrows are wind, of course. So now we're going to look at high pressure area. This is looking, head on, right? We see the sinking area. You're going to have divergence once it hits the ground. That's the side view. And up top view, you can see if the flow moves outward from the center to the periphery, Coriolis acts upon it, and it bends it to the right. This is the northern hemisphere, and you get a clockwise flow. Here we see side view of the low pressure system, air rising, so it's moving into the center, and it deflects to the right, creating the counterclockwise flow again for the northern hemisphere. Right? This diagram, I think, simplifies it and just clarifies it a bit better. High pressure areas bring clear skies, dry weather, gentle winds. Low pressure, cloudy, wet weather, strong gusty winds. So now throwing in the Coriolis. Okay, let's start here. And high pressure system referred to as anti-cyclone. Low pressure system referred to as cyclone, resulting in anticyclonic, cyclonic flow, respectively. Northern hemisphere, high pressure systems flow clockwise, CW. Lows counterclockwise, CCW. Counterclockwise. Southern hemisphere, high pressure systems flow counterclockwise, lows counterclockwise. But highs are still called anticyclonic, lows cyclonic in both hemispheres. What differs is the direction of rotation of the two hemispheres. So let's start here at the low pressure area. The pressure gradient force pushes the balloon inward. Coriolis turns it to the right. That's what we see here. Boom. The balloon is at the pressure that balances the forces. What's meant by that? This arrow this way is the Coriolis wanting to push outward, or push to the right, I should say. This is the flow of the wind wanting to go towards the center. So this arrow, you can see it here, this arrow is the wind wanting, the air wanting to follow the gradient and move from high to low, high being on the outside, low on the inside, but Coriolis is acting to deflect it to the right. So that's what this arrow is. So the result is you follow this path, because you can take these arrows and you have the same result all along the circular or elliptical path. And you then stay on that, and that's how you keep rotating. So this red arrow is the balance. So the balloon is at the pressure that balances the forces. It turns counterclockwise to stay on the pressure line where the forces are balanced. Now, sometimes you get a little spillage, and then you have, then you can create like a trough, what have you. Now let's come to the high pressure system. This arrow now is representing the wind wanting to go from regions of higher pressure to regions of lower pressure, but Coriolis is pushing it to the right, deflecting it to the right. So once again, we see it, the red arrow being where it is in balance. We're going to see something similar when we discuss geostrophic flow for oceanic gyres. The geostrophic flow is what balances the pressure gradient, only the pressure gradient determined by sea level height, and the Coriolis effect. So the balloon follows, just like over here, the balloon follows the clockwise path that keeps the forces in balance. And just to kind of pull this all together, summary-wise, in the northern hemisphere, right, you have a divergence at the bottom, a convergence at the top. It spirals down, and if you notice, the spiral is to the right, and you can see the movement to the right. This is clockwise, but anticyclonic. Spiraling up, so you have the divergence at the top, convergence below. Here it's convergence up here, divergence down there. It spirals up the right, and as it does so, here's the movement to the right, deflecting it to the right. Okay. And then it's just the opposite, and this would be a cyclonic flow. It's just the opposite. You're still going to have, a convergence at the top and divergence at the bottom for the high pressure system. It's just that in the southern hemisphere, it deflects it to the left. And you can see how they're opposite. Same thing here. They're opposite here. And so you get the flow to the left, the flow to the right, etc. Still going to have a convergence at the bottom, divergence at the top in both hemispheres for the lows. Convergence at the top, divergence at the bottom in both hemispheres for the highs. So this is how you get your low and high pressure systems. Different temperature, different pressure gradient due to different differences in temperature, which is due to unequal solar heating. Then the atmosphere moves, air in motion is called wind, and then you have Coriolis acting on it. So that's kind of in the nutshell. All right. Now let's move on to gyres. Here are some of the major oceanic gyres here. Warm water, cold water. Okay. This is, you'll notice, this is what? Anticyclonic. It's clockwise in the northern hemisphere. It's anticyclonic still in the southern hemisphere because it's now flowing counterclockwise. Here's your Antarctic circumpolar current. This is kind of a broad picture just showing a nice little gyre. And in both cases here, Coriolis deflects to the left in the southern hemisphere, to the right in the northern hemisphere. Now we can bring in with the Ekman transport. We'll discuss that momentarily. And the point of it is these major oceanic gyres, you have a convergence zone in the center, and with using the conservation of volume, the water in the center has to sink. You get a downwelling. If there are any nutrients in the upper layers, they're brought out of the photic zone. But the major oceanic gyres tend to be biological desert, very low productivity. And as it turns out, it's also concentrating plastic crap that humans keep throwing away. So this is just, I wanted to show, it's the same idea, right? You have a cold water, warm water, but this arrow here, this is the north equatorial current. This is the south equatorial current. You see how it's pretty much a straight line because you're near the equator. You get away from the equator and you start getting the bending, you start getting the deflection. Okay. Now, when we consider the deflection to the left this way and to the right this way in the hemisphere, you create a little void in between them, and there's your equatorial upwelling region. Also keep in mind there is an equatorial countercurrent, also an equatorial undercurrent, but the countercurrent goes from west to east. This is going east to west. You have west to east. This will change in strength depending on what cycle ENSO it is. And that's what I'm saying here in this caption I wrote here. The two gyres in the Pacific have a flow from east to west near the equator straight. This is due to little or no Coriolis effect as being near the equator. These are the equatorial currents that comprise the respective gyres in the Pacific. There is an equatorial countercurrent which flows west to east and which strengthens during El Nino events, which then depress the pickup line on this side. You get a downwelling, basically onshore Ekman transport with a downwelling, and the fisheries go south. Okay. Now this is an interesting diagram. So let's look at this. This is looking at it from above. Okay? Anticyclonic applied stress, convergence, and downwelling. Okay, I'll explain what this and the dot is in a moment. These double arrows here are the Ekman transport. Okay. Here we have cyclonic applied stress. Okay. Note the direction. This is clockwise, this is counterclockwise. So this is illustrative of the northern hemisphere. In the middle, you have a divergence with an upwelling, right? You see the water is flowing out. This is Ekman transport. That's the mass transport of water. It's flowing out from the center. So you create a void in the middle, you need to refill it. Conservation of volume. So you have an upwelling. This dot that you see here indicates water flowing at you. So it's coming straight at you. This X is water going down away from you in this example. Because you can see water is being piled up, moving towards the center. It has to go down. And that's what this is. This is a side view now. So this arrow corresponds to this arrow. This arrow corresponds to this arrow. Water piles up. Here is the downwelling. So this is flow coming at you. This is flow going away from you. Right? This arrow is this arrow. This arrow is this arrow. Flow is outward. Create a void in the middle. Upwelling. Again, this arrow is coming at you. This is going away from you. Okay. Now, this is very interesting because, and let me enlarge this a bit again. When you do vector multiplication, okay, whenever you multiply two vectors, called a cross product, okay, you might be familiar with the IJK rule, the right-hand rule. Right? Here's the right-hand rule. My hand in here. Right? This is IJK. So if I cross I and J, the result is this, right? Okay, now I'm not giving you guys the finger. Okay. So yeah, if I cross I, J, that's this way, right? Cross, the result is this way. Basically, whenever you cross two vectors, multiply two vectors, the resultant vector that comes out of that multiplication is orthogonal to the two vectors that were just crossed. Orthogonal means that right angle, 90 degrees. Normal is another way of saying 90 degrees. So orthogonal, normal, right angle, 90 degrees, all means the same thing, perpendicular. Okay? So whenever you cross two, this is backwards from my orientation. So whenever you cross two vectors, the resulting vector will be perpendicular. See how this finger is perpendicular to my index and thumb. So this would be I cross J gives you K. Right? I cross J gives you K. That's this situation here. Okay? I cross J gives you K, downwelling. The opposite is J cross I, which gives you minus K, an upwelling. 2 times 3 equals 3 times 2. But if I cross J does not equal J cross I, vector multiplication is not commutative. It is not. So another way to think of this is how many times you have a screw and you get your cordless driver and you want to put that screw into a piece of wood. So you put it into Titan and it spins this way, right? So it's spinning in this direction and the screw goes into the wood. Flip the switch, the machine rotates the other direction and the screw comes back out. That's an example of doing I cross J, giving you K into the wood, J cross I, giving you minus K out of the wood. So that's very important because that governs oceanic gyres. That governs it right there. So a pet peeve of mine is whenever I see, second grade math books and they have 2 times 3 and they go 2x3, I just want to scream because x is a symbol indicating a cross vector multiplication, a crossing of vectors. 2 times 3, 2 and 3 are not vectors, they are scalars. Use a dot product. It should be 2.3. So it just drives me nuts whenever I see that X for multiplication, but it's not vectors. You know, it's a pet peeve of mine. I know it sounds silly, but it is. So anyway, so this gives you kind of an idea of what's going on with the idea of convergence and downwelling for anticyclonic flows, and divergence and upwellings for cyclonic flows. Okay. So this is just kind of a quick little diagram to show you what's happening. You got North and South America on this side, Europe, Africa over on this side. So the prevailing westerlies are the black lines here. Okay. This represents, and I'll get to that in a moment, what's called wind stress. Wind stress is, I mentioned that briefly in the ENSO video, I believe, but the wind stress is basically the friction, the drag that the wind imparts on the water. Now, the wind stress, the force applied is parallel to the water's surface, but how the surface current responds is not in the same direction as the direction the wind is blowing. There is a slight deflection, okay? Slight deflection. Now, if you note, this is totally in the northern hemisphere, right? The equator is down here. Okay? So you got prevailing westerlies, and here are the northeast trade winds. So this is the deflection due to Coriolis. And usually the surface deflection is about 45 degrees approximately to the direction of the wind stress. This arrow here, that's perpendicular to the black arrows, that represents the Ekman flow. So now you add these up, right? These little flows here. Now when we get to the northeast trade winds, its deflection is still to the right. Ekman is still to the right. And you create a nice little gyra, and this water is going to pile up in the middle, creating this nice little convergence zone, and you're going to get a downwelling in the middle. So westerlies, still going to get deflection to the right. Northeast trade, still going to get deflection to the right, resulting in, because of wind stress, resulting in Ekman transport, which moves water to the middle, piling it up, creating a pressure gradient where now the water flows back outward. So some of it flows down, but some of it will flow horizontally. So now this is kind of showing a sort of in the 3 dimensions what's going on. Okay? So here's the Gulf Stream over here. Then you have the North Atlantic current when it gets up towards the Scandinavia region. Then you have the Canary current off Africa. Now you notice they've got a whole bunch of arrows here. What happens on the eastern side of a gyra is that the flow slows down, and it's much faster on the western side. It's called western intensification. There's a lot of reasons for that. It's very complicated physics and mathematics, but it does have to involve with the direction of the Earth's rotation. It also takes into account things as topographic steering, vorticity, and all sorts of stuff. I don't want to go there. As I said, I just want to present general ideas to what's going on here. I don't want to turn this into a graduate course. But we get the same idea. Okay, these black arrows here, represent Ekman transport. Ekman transport forms a dome, a mounding up of the water. So now if I look from here to, say, this is the bottom. If I look at this here, the water here is at a lower height than here. That means at this location, there is more pressure exerted on whatever that layer is. It doesn't have to be the bottom of the ocean. It could be a layer in the ocean. You're going to have more pressure here than here. Well, guess what? The pressure is going to create a pressure gradient from high to low, and water is going to want to flow down the pressure gradient. And then, you guessed it, Coriolis is going to act on it, turn it, and so on. So this is sort of like a self-perpetuating system. Now, you're going to have some horizontal flow down the pressure gradient outwards from the domed up center to the periphery, but there also will be downwelling. And the downwelling will actually drive down the pycnocline. I say thermocline, pycnocline. Right? So you get the downwelling that sinks, compressing the layers beneath, forcing those layers to spread. So there's your divergence there, right? So convergence here, divergence there. It's sort of like the flip of the atmosphere where you had the divergence at the, well, so you got the divergence at the bottom and the convergence at the top, with the top being the surface, the air, water interface. So that's what's being indicated here. All right, here we go. Geostrophic flow. Excuse me. Ekman transport piles of water within subtropical gyres. Surface water flows downhill and to the right, northern hemisphere, to the left, southern hemisphere. That's what I was just talking about. It flows down the pressure gradient. In addition to whatever downwells, it's going to be some that flows down the horizontal pressure gradient. The geostrophic flow is the balance of the Coriolis effect and gravitational forces. Friction generates the actual geostrophic flow. Okay, so I will tell you, it's not really readable, so I will explain what's going on in these figures here. Up here is where you have the domed up surface area here. Now, if you look closely, these contour lines would be the path of ideal geostrophic flow. But it doesn't always follow the ideal geostrophic flow. It follows the actual geostrophic flow, which is this dashed line here and here. So whatever the point is, wherever you're located at. Now, if you look here, this red arrow is the gravitational force because it's higher surface sea height here, means more pressure. It's going to follow the gradient from high to low pressure, but that's also driven by gravity. It's a gravity wave. Well, technically it's a gravity flow. And Coriolis, because it's flowing this way, wants to keep pushing it to the right. So guess what? The balance between the Coriolis and the gravity flow are basically in what creates the gyra. Okay, so now they take points here and they line it up with points here. So this is a side view. This is now looking down from the top. Okay? Once again, we still have the geostrophic flow, and the blue arrow represents the resultant. Okay? So you have domed up water here. Water some is going to downwell, but some is going to flow outward. As it flows outward, Coriolis deflects it, and then you have Ekman transport moving it towards the center again. And that occurs at all points. You've got Ekman acting all over the place. You note here the tighter contour lines here, indicating a faster flow, a steeper gradient. So this is faster flow. This is westward intensification, and it slows down this way. An analogy might be, the elliptical paths planets find. Kepler's law basically stated that the planet will sweep out equal areas in equal time. As it gets closer to the sun, it speeds up, and as it gets further away from the sun, it slows down. Of course, the sun's gravity keeps it in its orbit, but it's kind of that idea. So the gravitational forces resulting from differing sea level heights that create differing pressures on some horizontal layer. Just as for air, water will follow the pressure gradient force. This is also gravity driven, flowing from places where it's domed up because higher sea surface height exerts greater pressure downward than lowered areas, to areas where there's a low spot or a depression. In simplistic terms, this is what geostrophic flow is. Water's piled up, it flows down it, Coriolis acts on it, turns it to the right, northern hemisphere, Ekman transport piles it back up in the center. That's basically what's going on in a nutshell. In the southern hemisphere, it turns it to the left, but Ekman transport will still pile it up into the center. Okay. Because water flows towards the center, it piles up in the middle of the major gyres in the open ocean. These are called convergence zones, with resulting downwelling found in the middle there. I'm trying to sum up what we have to this point. The biological productivity is very low to poor, as any nutrients found in surface layers will be removed from the photic zone. This is why the middle of the oceans are referred to as biological deserts, but these gyres do concentrate all the plastic crap humans have created. There are some exceptions. Gyres where water flows outward from the center leaves a void in the middle to conserve volume. There's an upwelling in the center. The center are thus called divergence zones. The upwellings bring in nutrients and thus have good biological productivity. Example, the Gulf of Alaska has a counterclockwise gyre, so it has a center with divergence and upwelling. Generally speaking, wherever there is oceanic upwelling, there will be good biological productivity, be it in open ocean gyres or, as we're about to see, regions of offshore Ekman transport with resulting upwelling by the coast and enhanced productivity. And this, by the way, is where the great majority of oceanic biological productivity occurs, on the continental shelf. Once you start getting to the slope or the center, very rare. There is also an equatorial upwelling between the two gyres, the two Pacific gyres most notably. Mentioned in other videos was wind stress. Wind stress is the action of wind on water, especially large bodies of water. The force of the wind stress is always parallel to the surface of the water, and the wind will drag the water. Recall, and I basically made a little reference back to what was discussed in the ENSO video. I forgot to close the parentheses here. Close parentheses here. Okay. This does not mean the water flows directly out in front of the wind, i.e. the same direction as the wind. Rather, the resulting surface current tends to go off at approximately 45 degrees to the direction of the wind stress. That's the Coriolis forcing, left or right, depending on the hemisphere. The Ekman spiral and Ekman transport that occur in the ocean, but are the result of wind forcing. The stronger the wind, the greater is the mass transport of water, and the deeper in depth the spiral reaches. Okay, Ekman transport. This is the net movement of ocean water at right angles caused by the wind. Now, little pop quiz here for you. Is this diagram of northern and southern hemisphere? Answer northern because of deflections to the right. So now we have the wind blowing this way. The surface current, right? So there's a wind drag here, but Coriolis is acting on it, so there's the initial deflection to the surface current, about 45 degrees to the direction of the wind. So this is right at the surface. You go some layer below it, it's further deflected. Okay, we go below that, it's further deflected. It's further deflected. This is at successive layers going deeper in the water column. Note that the length of the arrows is shortening. It's getting less and less. Eventually, it even starts by pointing back at itself. Now, you have to keep in mind, the water itself is not spiraling. It's that successive layers of the water they themselves are being deflected by Coriolis. Now, this huge arrow here is the net transport of the water. Notice you have water going this way, the net transport. This is determined by integrating over the water column from 0, being the surface, to whatever depth z, it basically dissipates. So the stronger this wind is, the further down vertically in the water column, you'll find these movements, which means you have more water being net transported in this direction. Okay, so this is the spiral right here. That's the spiral. This is the transport. Okay. So this is now same idea. The Ekman transport is the overall water movement due to the Ekman spiral. Boom, boom, boom. Kind of see a little clearer here. You can see these little spikes here. You trace out this path. It does form a spiral. The ideal transport is 90 degrees from the wind. Transport direction depends on the hemisphere. This is showing it to the right. The wind's going this way. This is northern hemisphere. Southern hemisphere, with the wind going this way, it would be that way to the side. So this is sort of like a 3D look-see. This is a top view. Here's the wind. This is approximately 45 degrees, and here are all these arrows. And then when you integrate over the water column, the mass of this water column, you get the general mass movement of water, as you can see, 90 degrees to the wind. Just sort of like kind of showing a little, you can see almost looks like a Fibonacci spiral. But here's that spiral. Right? And boom, 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 boom. All the water here, net movement, and so on. I just kind of like this. I thought this was a cool little diagram. Wind friction currents and Earth's rotation. Okay, wind friction, right? The drag. The shallow flow drags and shears the water just below it. Heat losses make each deeper layer flow slower, but each layer still feels the Coriolis force. There's another thing, right? Again, showing here's all the spiraling, boom, 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 showing the net movement. But here's another point that's important to make that was not made here. The deeper the water flow, the less influence surface winds will have, which also contributes to a slower flow at depth. Right? You're down here, the further you go deep, the less influence this action is having on it, on whatever the flow is at that point. That's basically trying to say. So it's not just heat losses and friction that's slowing down the each layer's flow, the magnitude, but also the fact that it's further away. And so, yes, the friction is a loss of energy, a loss of efficiency, which will create a slowdown. So it's important to note that the water itself does not spiral. I made that point earlier, but I want to reiterate that. Rather, each layer is deflecting in response to the direction of the layer above it. So if this layer is going this way, that layer is going that way. And the angles, they're going to vary a little bit, but they'll be pretty consistent. Anywhere in the 20 to 45 degree realm, as indicated at the top here. So again, I'm just driving home the point. The spiraling, right, the flow slows down because of friction, heat loss, further away from the surface and the wind effect. And you can see this big, giant, huge arrow. Boom, that's the direction of the water. Okay, so now you can see how gyras form. Let me go up to a nice gyra here. Okay, we'll look at it from above. Higher water here, lower water there. Higher pressure here, lower pressure there. Water is going to follow down the pressure gradient. Coriolis acts on it, moves it to the right. So we get that directional change that helps create the gyra. But now, because also again, this is all wind, there's also wind acting on it, right? The wind is pushing the water to begin with, right? Whether it's the westerlies or the trades, right? Winds are pushing the water to begin with. So now you have Ekman transport pushing the water back towards the center, basically keeping this in a perpetual system. Domes up again. Yes, there's going to be some downwelling at the center, but there's some horizontal flow down the pressure gradient. Coriolis pushes on it. Ekman transport piles it back up, as we saw with the spirals. But the whole thing is a result of wind forcing. Where is that? Wind forcing. That's what drives this whole thing. Wind forcing. Okay. Now let's consider situations where we're on the continental shelf and get near shore. Ekman transport also plays a role in coastal dynamics, not just the open water. This is what is known as onshore Ekman transport. It's right here, right? Because the wind is going this way. Winds tend, sometimes will often be parallel to the shore. So if the wind is blowing this way, again, northern hemisphere, the Ekman transport is to pile the water towards shore. Well, conservation of volume. Water moves this way, not going to keep piling up. It has to flow back outward. So that's what this is. You get a downwelling. Downwelling as well, and the downwelling will cause the pycnocline to depress. So there it is. This is a downwelling. So onshore Ekman transport results in a downwelling at the coastal processes, which is not good for biological productivity. So the pressing of the pycnocline, downwelling, not conducive to biological productivity. This is what happens to Peru during El Nino. There's onshore Ekman transport, depressing the pycnocline, downwelling, no nutrients, fisheries go belly up. Contrast that with wind going the other direction. So now we have wind blowing this way. The net transport is this way, right? So now you get waters moving offshore. So now you get an example of, oh, hang on, that one. Not ready for that second there. So now you get what's called offshore Ekman transport. So the pycnocline becomes shallower. This is supposed to represent, this is from here to here, and that's supposed to represent the pycnocline. And this actually rises up, just like we saw during La Nina events there. Right? So now you get the reversal of the winds. You see how it's going together? When the wind blows a certain direction, you get the onshore Ekman transport, that warm blob of water depressing the pycnocline, no fisheries. You get a downwelling. Winds reverse, the Indonesian low shifts further west. Now you get the wind forcing going back the other way. Now you have offshore Ekman transport creating the shallowing of the pycnocline and an upwelling. Right, it's indicated here. Right, the upwellings here, and that's good for productivity. Upwelling bringing nutrients, resulting in good biological productivity. So I'm trying to, with these videos, I'm trying to tie in together how all of this works. It's a beautiful system, complicated to understand, but we nevertheless have been able to figure this out. So again, I'm tying in all these oscillatory systems in the atmosphere, with atmospheric forcing, what the ocean is doing, the ocean responding to that, what the ocean does and then drives the atmosphere. It's all tied together. And this is just kind of puts the two together. Right? Water moving offshore due to Coriolis effect to get upwelling, good productivity. Wind's going this way, wind goes this way. Water moving onshore, you get downwelling, poor productivity. And if the coast is over here, then you'd have the upwelling here and the downwelling there. And this is just all together in one big splat. It's pretty much saying the same thing I've been saying over and over again. The currents do not spiral, they just flow horizontally in slightly different directions at increasing depth due to the Coriolis deflection. Current strength declines with depth due to drag further away from the surface and is indicated by the shorter arrows here. So the spiral is just the spiraling of the shortening current flow's magnitude is really all I'm talking about here. So if you wanted to look at this, you can pause the video. It's just kind of a little summary, put it all together for what I've just been discussing. So I wanted to show you this. Here's the north equatorial current, south equatorial current. It starts to deflect as soon as you get away pretty much from the equator. Here's the countercurrent. It goes this way. It hits Panama and has to move somewhere. Okay, but it goes this way. This strengthens during El Nino and weakens during La Nina. Here's this convergence zone, right? Boom, boom, boom. We got this Ekman transport pushing stuff to the center. Here's the convergence zone. Now here is the gyra in the Gulf of Alaska. See how it's counterclockwise? Clockwise here, counterclockwise here. That means this is going to be a divergent zone in the center at the surface with upwelling, and no surprise, the Gulf of Alaska is very productive waters. For open oceans, probably has some of the highest productivity of all the oceans. Aside from the Antarctic, wait for it, divergent zone down in Antarctica, where the thermohaline current, the North Atlantic deep water, eventually makes its way up to the surface. The Antarctic divergent zone brings up all the lovely nutrients. Upwellings mean good biological productivity. Now, the 5 plastic gyres, because I just, is that right? You have a convergence zone here. All the plastic shit that's in the ocean converges in the gyres. So North Pacific gyre, South Pacific gyre, North Atlantic, South Atlantic gyres, and then the Indian gyre. And then a little description. Right? Gyre is a whirlpool. It's not really a whirlpool. That's not a good word there. It's just simple rotating flow of water. Whirlpool indicates, you got some sort of suction going on at the bottom there. It's not a whirlpool. So that's not a good word. Home right, the Great Pacific Garbage Patch, I'm sure you've all heard about. 3.2 million tons of trash of the size of Texas, located between Hawaii and California. Research between Bermuda and the Azores document floating garbage, soup of microplastics. I've done some videos discussing plastic and microplastics. I got more in the that I'm working on. That'll be soon. Now this is where it starts getting the impacts on wildlife. 44% of all seabird species documented with plastic in or around their bodies. That's just horrible. Plastics have entangled birds, turned up in fish belly, whales, any sea creature. They're pretty much finding plastics in their digestive system. Turtles, whales, sea lions, pinnipeds, you name it. Fish, birds, it's just turning up. And when they were looking for that Malaysia airline flight 370, they necessarily didn't find the plane, but they found garbage. So it's an indictment of the wastefulness and just the utter total crap treatment of the environment that humans have exhibited. So I just wanted to show you that. But here is an example where the physics will have to determine what some of the manifestations we see. So anyway, I hope you found this informative, and I hope you're able to get a better handle on the rotating system, be it atmospheric or the gyres. But the key point to keep in mind is it's driven by a pressure gradient force. And then you have Coriolis acting on it. The added thing with the ocean is that you then with the wind stress that creates the gyres, right? Because the wind stress is pushing the water, be it the trade winds or the westerlies, it pushes the water responds. Coriolis deflects the water. You have the spiral going down depth, resulting in Ekman transport that will keep the water piling up in the center if it's a gyre with a convergence zone, or if it's a gyre with a divergent zone like Gulf of Alaska, then you have constant inflow. As the water is constantly moving out from the center, you're going to have constant upwelling to fill in the void, if you will. So you have that little extra thing there. So between the Coriolis and Ekman for oceanic gyres, Coriolis pressure gradient, right, for atmospheric highs and lows, clockwise, counterclockwise, clockwise, updraft, downdraft, and so forth. So thank you for your time, and we'll talk soon. Hey folks, this is Jim here reminding you to please subscribe to my channel and please share my videos with others. Also remember to click the bell so that you know when I drop in a new video. I also ask that you please consider becoming a patron of my channel and support the work that I do by going to patreon.com/Science Talk with Jim Massa, each word separated by an underscore, and becoming a patron. It's asking for as little as $3 a month, cost of a cup of coffee, to support the work I do and keep my informative videos coming your way. Thank you for your support.